Deep inside every internal combustion engine, there are these small, unassuming parts working under conditions of just unimaginable violence. They are truly the unsung heroes that are responsible for harnessing the raw power of combustion. Today, we're going to do a deep dive into the engineering of one of the most critical components of them all, the piston ring. To get an idea of the world these things live in, think about the crushing pressure at the bottom of the ocean. Okay, now imagine even more than that. Inside the combustion chamber of a modern engine, pressures can spike to over 100 bar. And in a high-compression diesel, that can shoot past 200 bar. That is just an immense, explosive force happening inside a tiny metal can. And if that wasn't enough, at the exact same moment, peak temperatures during that combustion event can flash to over 2,000 degrees Celsius. We're talking about an environment of extreme heat and extreme pressure, and it's happening thousands of times every single minute. So that brings up a huge engineering question, right? How do you contain all that incredible energy while a piston is just violently flying up and down in its bore? How do you create a dynamic seal that's strong enough to hold back that force, but still allows for motion with the least amount of friction? Well, the answer lies in the really precise design of the piston ring. So to really get how they work, we've got to first understand what they are and where they live. Let's break down the anatomy of the piston and its rings. Okay, so what you're looking at here is a modern piston. That top surface, that's the crown. It's what faces the fire of the combustion chamber. Now, see those precisely machined grooves down the sides? Those are called the ringlands, and that's exactly where the piston rings sit. And also, take note of those little oil drain holes. They play a super critical role that we'll talk about in just a minute. You'll find that most modern car engines use what's called a 3-ring pack. Now, it's really important to get this. These aren't 3 identical rings. Not at all. Think of it more like a specialized team, where each member, each ring, has a very distinct and absolutely critical job to do. All right, so that top ring, that's your primary compression ring. It is the frontline soldier, taking the full brunt of all that combustion pressure and all that heat. Its one and only job is to seal that explosive force. The second ring, the one in the middle, it's a bit of a multitasker. It acts as a backup seal for any gases that might sneak past the first one, but it also starts the process of wiping excess oil down the cylinder wall. And finally, that bottom ring is the dedicated oil control ring. Its entire life is focused on oil management. Now, this oil control ring isn't just some simple piece of metal. It's often a pretty complex multi-piece assembly. You can see it here. It usually has 2 thin steel rails, and they're separated by an expander piece. This whole setup allows it to apply this really precise and consistent pressure against the cylinder wall, scraping the oil film down to the perfect thickness and letting any extra oil drain back to the crankcase. So, we know what they are, but how on earth do these simple-looking split rings create such an incredibly effective seal? Well, this is where the physics gets really, really clever. It all comes down to a principle called gas-assisted sealing. So picture this. Combustion happens, and that immense pressure doesn't just push down on the piston. A small portion of that high-pressure gas actually flows into the ringland and gets behind the top compression ring. That pressure then pushes on the back of the ring, forcing it outwards against the cylinder wall with incredible force. The engine is literally using its own power to perfect the seal, and it does it dynamically with every single power stroke. It's just a beautifully efficient system. Now, you might be thinking the ring is just scraping against a dry metal cylinder, but that would lead to immediate, catastrophic failure. Instead, it relies on something called hydrodynamic lubrication. The cylinder wall has this fine crosshatch pattern machined into it, and its job is to hold a microscopic layer of oil. The rings don't actually make metal-to-metal contact. They're basically hydroplaning on this thin, pressurized film of oil, which dramatically reduces friction and wear. So let's just recap for a second. This tiny little ring pack is juggling 4 absolutely critical jobs all at once. It seals combustion pressure to make power efficiently. It controls oil to keep it from burning up in the combustion chamber. It acts as the main bridge for transferring destructive heat away from the piston and into the water-cooled cylinder walls. And finally, it helps stabilize the piston, preventing it from rocking in the bore. Okay, but what happens when this perfectly engineered system starts to wear out and fail? Well, the consequences are immediate, and they can really snowball through the whole engine. The number one failure mode is a condition known as blow-by. And really, that's just the technical term for when the seal isn't sealing anymore, and those high-pressure combustion gases leak right past the rings and into the engine's crankcase, which is where they absolutely do not belong. So what does that actually mean for your engine? Well, the most immediate result of low-buy is a loss of compression. If the pressure that's supposed to be pushing the piston down is instead leaking away into the crankcase, you get a direct and very noticeable drop in engine power and thermal efficiency. The engine is literally just wasting the energy it's creating.
All right, so let's get out of the textbook and onto the garage floor. How can you actually spot failing piston rings in the real world? Well, there are a few classic telltale symptoms you can look for.
One of the biggest red flags is blue smoke coming out of the exhaust, which means you're burning oil. But here's the tricky part. As the folks at Auto Repair Guys point out, this symptom can be caused by two common culprits. It could be worn piston rings, or it could be worn valve stem seals. The trick is knowing how to tell which is which. And this right here is the key diagnostic difference. If your rings are shot, the oil control has failed, and the engine is going to burn oil pretty much continuously while you're driving, and it often gets worse as you rev the engine higher. In contrast, bad valve stem seals typically cause a puff of blue smoke right on startup, or maybe after idling for a while at a stoplight, and then it usually clears up as you drive. This distinction is absolutely crucial for an accurate diagnosis.
The problem really presents itself as a full cascade of symptoms. You'll feel that loss of power. You'll notice you're having to top up the engine oil all the time. You'll see that continuous blue smoke. The excess oil can foul your spark plugs, which causes misfires, and all that blow-by gas will start to overpressurize the crankcase. When you see all these things together, they paint a very clear picture of a failed ring seal.
And I've got to stress this is not an issue you want to ignore. Those acidic blow-by gases get into your engine oil and they contaminate it, basically turning it from a high-tech lubricant into an abrasive sludge. That sludge then gets circulated through the entire engine, rapidly accelerating wear on every single moving part, and that can eventually lead to catastrophic failure. Which kind of brings us to a final thought. As engineers keep pushing for more and more power from smaller, turbocharged engines, cylinder pressures are just rising to levels we've never seen before. This puts an incredible strain on this tiny little component. So the ongoing challenge is one of material science and design. How do you develop new coatings, new alloys, and new ring shapes that can reliably seal these insane forces for hundreds of thousands of miles? The evolution of the humble piston ring, believe me, is far from over.